Now we will be discussing about a different type of bond, which is the metallic bond. Yeah. Now, metals represent another type of extended system, so it's also in a lattice, just like the ionic systems that we've discussed before. However, the chemical bonding of a metallic bond with ionic bond is totally different. In metals, the atoms are also they're arranged in a lattice, yeah, but they don't have a positive charge and negative charge. If you remember the picture before, they are not alternating like this in, for instance, a cubic lattice. Yeah. Now, for metallic bonds, it's not like this. Oh, sorry, it's not like this. But instead, what we have is the nuclei. Yeah, so several of nucleus and some fraction of their electrons. They comprise a positively charged, what we call as core. Now, this is localized at the lattice point. So if you have a cubic lattice, let me draw a cube. There's a cube over here. Like that. Now, we have a nuclei and some fractions of the electrons that forms a core. Yeah, this is what we call a core. And because mostly it's nuclei, then mostly it's positively charged. So we can write down here is positive, 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 like that. Okay? Now, while the other electrons they move freely throughout the whole array. So here you can imagine sort of like a cloud of electrons that moves freely around the lattice. Yeah. Well, you can imagine it as like a sea of moving electrons. Okay, so that's the main difference. So let me write negative charges over there. In ionic bonds, again, the difference is for ionic compounds, what we have is alternating plus, minus in a lattice. Yeah. If you forget about this, you can take a look at the previous segments where we talk about the ionic compounds. Now, for metallic bond, it's also a lattice arrangement, but instead of alternating positive, negative charges like this, you have a mainly positively charged core, and you have a sea of negatively charged moving electrons. And therefore, this is why in the macroscopic level, you know that metals are conductive. Yeah, they can conduct electricity, and they're also shiny. They're reflective. Yeah, that's why we can see these properties in the macroscopic level. So you can imagine that if you have piece of metals, for instance, you have a piece of, say, metallic iron, yeah, a piece of iron, Fe, like that. In microscopic level, you can see that they are shiny in appearance, and also you know that one of the properties would be that it is conductive. It can conduct electricity, but in the microscopic level, now you also understand what's happening, yeah, because you have a sea of moving electrons. That is why it is conductive and shiny. And in the core part, we have mainly nuclei, which is positively charged, and also a little bit of fractions of the electrons. So this is the second type of the bond. First one was ionic compound, and now this is the metallic bond that, of course, you can see in metals, in pure metals, yeah, Fe, nickel, chromium, zinc, and etc. Any kinds of metals that you can think of. Now on to the third one, which is the covalent compounds. Covalent compounds comprise covalently bonded atoms in the structure, and these compounds, they comprise really large examples of molecules that we are going to talk about throughout the entire lecture within this semester. Yeah, the main characteristic for such compounds, is there is a sharing of electrons. And this happens between two adjacent atoms. Yeah, and this is where you can see the difference between covalent compounds with, for instance, a metallic bond that we just discussed. Let's take an easy example. Water, H2O, it's H. You have one electron for H, like this. Yeah. And for oxygen, you have also one electron over here and one there. And later we will also talk about how to draw such structure that you will know as the Lewis structure. And oxygen actually has 6 electrons. So we have one here, 2 there. We have to draw another 4. Yeah. I will not go in the detail for now for Lewis structure, but later we will discuss it in depth. Yeah. But for now it's like this. And you can also write this down into, or draw this into this structure. Okay? So what can you see now? What can you compare between this drawing over here and the picture over here? One line equals to 2 electrons, or what we call as a pair of electrons used for binding, or used to form a bond. Used for forming a bond. Okay? So they share electrons. The hydrogen here and the oxygen over there, they share these 2 electrons to make one bond. And the hydrogen here with the oxygen, they share 2 electrons here to make one bond. So one bond equals to a pair of electrons that are used for binding or For short, we can also refer to this as a bonding pair. Bonding electron pair. And this one, because they are not used for binding, we normally call them lone pair electron. Okay, so again, one line or the bond is actually consists of a pair of electrons that are shared together between the two adjacent atoms. It could also be same atoms, yeah. It doesn't have to be different like this. We can also have, say, oxygen, like this, yeah. So if you want to draw this as dot structure, then it's actually O, like that. Yeah, and as oxygen has 6 electrons, so if you just take a look at this oxygen, it's 1, 2. So you have to draw the remaining 4 because it has 6 electrons. Let me draw it in a different color so you can tell which one is the lone pair and which one is the bonding pair. So this one is the lone pair, and we have, in this case, 2 bonds. 2 bonds, meaning there are 4 electrons used together, yeah, in a shared manner between this oxygen and the other oxygen. And this is the hallmark of covalent compounds. And from this, you can go to more complicated structure, yeah. For instance, let me draw the combination between nitrogen and oxygen. You can have N2O. You can have NO. Okay? You can have NO2 and 2O3. So these all exist in nature. Okay? So based on this, you can try to check their structure first in textbook or in the internet, because we do not yet learn about how to draw the Lewis structure. So you can first just now Google them. But overall, you will be able to see how it is similar to what we have discussed here. So we have 2 adjacent atoms and there are bonds between the atoms. Could be single bond like this. It could be multiple bonds like this. Normally it's up to 3, yeah, multiple bonds. It's very rare to have 4. Normally we don't really discuss more than 3 bonds. The way we name them, it's a bit different with what we have discussed in the ionic compounds. So for covalent compounds, you always... Okay, let me write this first. For covalent compounds, you always have to use the prefix. Or maybe there's no hyphen. Prefix that will give you an idea about the number. Okay? And also, the first element normally retains their full name. So retains its name, while the second element, if you have two different elements or 2 different atoms, will end in "ide," yeah, as the suffix double F, right? Okay, as suffix. Okay, and then don't forget, you have to put the prefix as number, except for mono. Yeah, we don't really, except for mono. Mono, you don't really have to, if it's only one, yeah, you don't really have to say that it's mono, especially when it's in the beginning. Okay, so let's name 1, 2, 3, 4, 5, 6. Okay, let's name them together. The first one would be di-nitrogen. If it's in the second elements, we can use the mono, yeah? And because it's oxygen, it becomes oxide. Okay? Di-nitrogen because it's 2 nitrogen, and oxygen become oxide because it has to end in an "ide" suffix. So it's dinitrogen monoxide. Second one would be, now in this example, you will see that you don't have to put the mono, especially in the first element. It's just nitrogen monoxide. This one, this guy. Nitrogen monoxide. Third one is, let me move here, nitrogen dioxide. Which one is that? It's this one, nitrogen dioxide. And then fourth one, di-nitrogen, because there's 2 of them, trioxide. Which one is that? It's this one, di-nitrogen trioxide. Moving on, the fourth one is dinitrogen. If it's 4 like this, you say it's tetra, yeah? Tetraoxide. And if it's 5 like this, dinitrogen penta, or pentoxide. Yeah, this one also, I will revise this. It's tetraoxide, or normally we call it tetroxide. So you see it's different for covalent. Yeah, it's different for covalent compounds. In this case, it's very important to put the number. Yeah, unlike the ionic compounds, where sometimes you don't have to put any number at all. And how we name them is that the first element retains its full names like that, while the second elements end in "ide." Okay? Now, covalent compounds normally, usually, oh, wrong pen. Usually, they are all nonmetals, yeah. So, for instance, N and O, H and O, H, O, N, and any combination of them. Carbon, yeah. Carbon is one of the most popular one. Also, of course, you must know this compound CO2. Yeah, how do we name this? Carbon dioxide. Okay, carbon dioxide. It's very common. You know it already, but now, based on this, oops, I don't meant to erase it. I was meant to point at it. Sorry, okay. So, carbon dioxide, now you know how it is named. Yeah, oxide, like this. Of course, there are so many other different examples. Go look for yourselves and try to name them. You can take a look at textbook. You can take a look at different sources in the internet. And if you have any questions, of course, we can discuss it during our synchronous session. Okay?